So before we begin the concepts of rolling motion, we have to learn what the angular position, the velocity, angular velocity, and the angular accelerations are. So this chapter deals about not the translational motion of objects, but the rotational motion of the objects. What does it mean? If you have an extended object like a wheel, you see in here, when the wheel rotates around a fixed axis, the axis in this picture is the center of the wheel. Okay, how do you measure the rotation? Is rotation a displacement? In some sense. If you think about the points on the rim, right? The points on the rim of this wheel, rim ne biliyorsunuz değil mi? Çevresinde. Tam dönen bir nesnenin en kenar kısmına rim diyoruz, tamam mı? Rim of a wheel, kenar kısmı, en uç kısmı. Any points on the rim, right? Will relocate itself when the wheel is rotating. Okay, so there is some sense, there is kind of relocation. There is kind of motion of the points, but there are many points on the wheel, right? Just concentrate on the point, on the special point on the rim. When you rotate this wheel, some amount, right? This point will go from here to this position. What kind of motion of this point is doing? That we have seen, it is a circular motion, right? If the wheel rotates with a uniform velocity, right? This is kind of a uniform circular motion that we already analyzed in chapter 6. How do you measure this relocation of this point? If you measure from the center, right? If you measure from the center, this distance does not change when the point comes from this point to here. The distance to the center is not changing, right? So just measuring its distance to the center is not a good point of measuring the relocation of the point, right? But if you measure this angle, that this line connecting the point and the center makes an angle with the horizontal line, the x-axis. You can measure always this angle. And this angle is one of the best, measuring this angle is one of the best way to give about angular position of the point. Okay? So by measuring these angles of the points on a rotating object, we can in some sense measure their position, and this kind of position is called angular position. Okay, so you make this difference with the linear position. The linear position is the position of any point or an object from a center, from an origin of the coordinate system, right? But in this kind of motion, since the point is rotating all the time, of course, after some time, if it continues to move, after some time it will come to the same position. Am I right? It will come to the same position. All right? But when it comes to the same position, can you say that it is never relocated or it is never moved? But you can say that how many turns does it do, right, when it comes to the same point. So in some sense, measuring this angle, theta, or measuring the number of revolutions is kind of, right, talking about its angular position. So let's first make this definition. The angular position of a point on a rotating object is just its axis connecting its line, connecting to the center, this line, right, makes an angle with the horizontal line. This horizontal line is the x-axis. All the time, this horizontal line is there, fixed. When you measure this angle what you do is you give its angular position. That's it. So the angle can be measured in terms of degrees, or it can be measured in terms of radians, right? One revolution, this angle, one complete. Let me talk about this. Let's extend this axis. Okay. What is this angle? From here to here, it's pi. Pi radians. You have to state the unit. Okay. If you're giving the angle in terms of radians, it is pi radians. What about in terms of degrees? 180 degrees. Okay. So that means pi radian is completely equal to 100 degrees. Okay. So we already make two different units for the angular displacement or angular position. One is radian and the other is degrees, and this is the conversion between them. What about the pi? What is pi? 3.114. Almost. 3.114 radian is equal to 120 degrees. Okay. What about one revolution? The angle of one revolution in terms of radians, it is 2 pi, or it is equivalent to 6.28 radians, and it is equal to 360 degrees. Okay. So if your object, the point, is rotating all the time, also you can give the angular displacement in terms of revolution. Revolution is another unit for angular position. Okay. So then you can easily say one revolution is equal to, in terms of degrees or radians, 2 pi radians, and it is equal to also 360 degrees. So there are already 3 different units for angular displacement. One is revolution, one is radian, and one is degrees. I don't know if there are other units for angular position. Okay, that's all about the angular position. So, but the thing is, when you measure the angles, in which direction the angle is positive? There are 2 directions for clockwise and counterclockwise. Counterclockwise is the positive direction for the angular measurements. Okay, if you are measuring in this direction, if you are measuring from here to here, okay, from here to here in this direction, in this way, then you're measuring the angles in positive directions. If you're measuring the angles in this direction, you're measuring in negative. Okay, that means if this angle is 60 degrees, then the point, the same point, symmetrical point here, its angular position is minus 60 degrees. Okay, because you're measuring it in the clockwise direction. Clockwise direction is always negative. Where the clockwise we take as positive, rotation in terms of measuring the time in our clocks, but in math it is the negative direction. It's just the convention that you cannot do anything about it. All right, so there is also this relation between the linear displacement, okay, and the angular displacement. And a linear relocation, or the spatial relocation of the point when it comes from this point, okay, when it comes go from here to here. If it is theta degrees or theta radians, whatever, it is the angular position. What about its linear displacement or linear distance that the object, the point, takes from going from here to here? It is the length of this arc, right? It is the length of this arc. What is the length of this arc? If this wheel has a radius r, we know from the geometry that this arc length, we call it as S, is nothing but equal to r times the radius of the wheel times theta in terms of radian. This is important. Not in terms of degrees, not in terms of revolutions. When you're calculating the distance S, the arc length, you have to use the radians. Okay? Because the one complete circumference of a circle of radius r is 2 pi r. 2 pi times r. And 2 pi is in terms of radian. So you have to make this difference. S is called arc length. And the other thing is, if this wheel is rotating with some speed, right? If it's rotating with some speed, then we are ready to talk about the angular velocity. If it's the point's position is given in terms of angles or theta, then I can always talk about the angular velocity, because how this angle is changing in time. This is called the angular velocity of the point, or the angular velocity of a rotating object. Any object which rotates around an axis always have a definite angular velocity. Okay? And one important thing is that if this object, this point, let me say, this point is rotating with an angular velocity of omega, omega is the notation for angular velocity, then any point, any other point on this wheel has the same angular velocity. Okay, if any point makes delta theta radians in 1 second, any other point on this wheel, be it on the rim or on any parts of the wheel, every point has the same angular velocity. Okay? So the angular velocity is not only for one point, but the angular velocity is for all points of any rotating object. And the unit for it is radian per second, because if you're measuring the angular displacement in radians, then you can also measure the angular velocity in terms of degree per second, okay? Or revolution per second, or revolution per minute. All the time you see on electrical motors, in 22 volts, this motor makes, let's say, 1000 RPM. RPM is the short notation for revolution per minute, RPM, revolution per minute. All kinds of electrical motors are given in terms of revolution per minute, usually. You can always convert that RPM in degrees per second, in radian per second, whatever. Well, an immediate example, Mercury, the planet, the first planet on the solar system, takes only 88 Earth days to orbit around the Sun. And if you assume that this orbit is a complete circle, it's a circular, then what is the angular velocity in radians per second? Mercury in its orbit around the Sun. So what was the definition of angular velocity? You can immediately write delta theta divided by delta t. Okay. What about delta theta? If the Mercury makes one complete rotation around the Sun, right? What is the angular displacement in terms of radian? 2 pi. And you will divide it by, since you have to find this velocity in terms of radian per second, you have to convert 88 days to seconds. And 1 day is 24 hours, right? And 1 hour is how many seconds? 3,600. So if you calculate this, whatever the value, I think I have already calculated as 8.3 times 10 to the minus 7 radian. Radian per second. Okay. That this angular velocity I have defined as the average angular velocity, but there is an instantaneous angular velocity. That means, well, if you see any rotating object, all objects are not rotating, of course, with the same constant angular velocity all the time. And sometimes the objects may change its angular velocity, right? And the instantaneous angular velocity is this limit, and in terms of calculus, this is shown as d theta over dt. Okay, and if you know the theta in terms of time, then you can easily calculate the angular velocity. If theta changes, let's say, with this 2 pi t square. Okay, let's think about a point or any angular, any object rotating with this angle theta, depending on time. Okay, what can you say about the angular velocity of this object? So immediately you can calculate the angular velocity by taking the derivative of this theta with respect to time, and it makes 4 pi times t. The angular velocity is changing also in time because it is a function of time. Okay, this is the instantaneous angular velocity. And again, there are two directions for the angular velocity. Okay, one is in the counterclockwise direction. An object may rotate in the counterclockwise direction or in the clockwise direction. If the object rotates in the counterclockwise direction, then its angular velocity is positive. If it's rotating in the other direction, its angular velocity is negative. Now comes the definition of period. The definition of period is the time required to make one complete revolution. And it's unit, of course, in seconds in SI unit system. So one period is time requires for one complete revolution. Okay, 2 pi rotation. So if you want to express a relation between the period, the angular velocity, and the angle, this is the relation. Then omega, by definition, is nothing but the total angle divided by total time. And since one revolution is 2 pi radian, and the time for one revolution is period, which is called with t, capital T here. So there is a relation between omega, the period, and the pi. T, if you are given the angular velocity of an object, you can easily calculate its period. Okay, its period is just 2 pi divided by omega. Next, you may have a changing angular velocity, right? Just like we had a change in the velocity in the linear motion, and this change was measured as acceleration, right? Because the acceleration is nothing but the change in the linear velocity. Just like this, we may change in the angular velocity, and this change in the angular velocity is known as the angular acceleration. Okay, and the angular acceleration, the average angular acceleration, is nothing but delta omega divided by delta t. It's the change in omega in time, and its unit is in terms of SI, in SI unit system, in terms of radian per second square. If you have a record, what the record is? Clock. A record spins at 33.33 RPM. As I said, RPM is revolution per minute. One revolution in 60 seconds. Convert this to radian per second, and we have CD CD players in your computers, it's spinning at 22 radian per second, and you have to convert this also into RPM. So there are two conversions. So 33.33 RPM means 33.33 revolution per minute. And one revolution, we know, is 2 pi radian. And 1 minute is 60 seconds. If you multiply this ratio by 33, you will get almost 50 radian per second. So you do the reverse conversion. In the second case, we have a CD spinning at 22 radian per second. And 1 radian is 1 revolution per 2 pi. And in terms of minutes, 1 second is 1 divided by 60 minutes. So you multiply this by 23, and 60 divided by 2 pi makes 210 revolution per minute. So almost how many times larger in angular velocity? I don't know, but maybe 7 times larger speed, right? Almost 7 times, right? About. So a CD is spinning almost 7 times larger than a plaque record. That means the amount of information it conveys to the computer is, we don't know. Of course, record is not transferring the information in terms of bits. It's a different thing. Okay, so the instantaneous angular acceleration, again, is you can express in terms of the time derivative of omega, the ray angular velocity. It is d omega over dt. Remember that example that I have given for 2 pi t square, if the point or an object rotates its angular position in 2 pi t square, and its angular velocity is 4 pi t, and its angular acceleration is 4 pi. Take a second time derivative. In terms of the position, angular position, this alpha is equal to d square theta divided by dt square. Remember, in linear motion, the linear acceleration was the d square x divided by dt square. It's the linear second time derivative of the linear position. But in the case of rotation, it's d square theta over dt square. So there's a correspondence between theta and x, omega and v, linear velocity, and a, the linear acceleration, and alpha, the angular acceleration. Well, we will have these examples of wheels, okay, fixed wheels that can freely rotate around an axis, and attached to this masses with different masses attached with a string. When you release an object, for example, in this case, from rest, you will see that this spinning wheel will have some angular velocity, but this angular velocity, when the object falls down, will change, right? It will increase because of the force. So this angular velocity can be expressed in terms of the initial angular velocity plus alpha times t. This alpha change in the angular velocity or the angular acceleration happens because there is always increasing speed of the rotating wheel when the object falls down. Okay, so this is the kinematics of the angular velocity for a constantly changing angular speed. Okay, so you see these quantities in linear kinematics and rotational motion. We have x as the linear displacement in linear kinematics, but in rotational kinematics, theta is the angular displacement, angular position. This is linear position, and this is linear velocity, and this is angular velocity, and a is the linear acceleration, alpha is the angular acceleration. So when we make these rotational kinematics equation comparing to linear equations, you can always use this linear expressions, okay? Since v is equal to v0 times a times t in angular rotational kinematics, this is replaced by omega, and a is replaced by alpha, and t is the same, okay? If you have a constant acceleration, constant angular acceleration, this is the expression for angular velocity. Again, if you have a constant acceleration, this is the expression theta is equal to theta 0 plus 1/2 omega 0 plus omega times t, or omega 0 times t plus 1/2 at square is the angular position for rotational kinematics having a constant angular acceleration. If your rotation has a constant angular acceleration, this is the expression for theta. Remember, this was x is equal to x0 plus v0 t plus 1/2 at square in linear kinematics. And also we had this, if you know the initial velocity and the final velocity and the displacement, you can find alpha a, the linear acceleration, or vice versa, whatever it is. So we had this expression, the same kind of expression we have in rotational kinematics. You replace v by omega square, v0 square by omega 0 square, and a by alpha, and x theta, x0, theta 0. So everything can be expressed when if you are, remember the linear kinematics equation, everything can be replaced by the angular quantities. And these equations are valid as long as we have a constant angular acceleration. Okay? So in the case of constant angular acceleration, these three equations or four equations are all equations about the kinematics of any point in the angular motion. An example, a windmill is spinning at 2.1 radian per second and slows down with an acceleration of 0.45 radian per second square. How long will it take for it to stop? So you have alpha, you have omega, and you have omega 0 initial angular velocity, and you have final angular velocity. Final angular velocity is 0 because it says when it comes to a stop. So by just using this first equation, you can easily solve for t. It takes 4.7 seconds to come to a stop of this windmill. What is windmill? Do you know windmill? Rüzgar gülü. Another example, again it's a simple example that you can check at home. There is a spinning ball, and the spinning ball changes its spinning from initial angular velocity to a final, and you will calculate the angular acceleration, and from that you will calculate how many degrees or how many radians does it do in its motion, vice versa, and whatever it is. Okay, I will leave it to you.
You said that the angular acceleration is 4 pi.
That was an example, yeah, 4 pi.
It's not a constant.
No. It was an example. Just if you have an angular, displacement given in terms of time, this is just an example. Then you can calculate the angular acceleration from this by taking the second time derivative of theta. Okay. This is just a special example. So one example, a propeller of an airplane is at rest when the pilot starts the engine, and its angular acceleration is a constant value when you start the engine. 2 seconds later, the propeller has an angular velocity of 10 pi radian per second. Through how many revolutions has the propeller rotated through during the first 2 seconds? That means what is theta? Or, well, what is theta in terms of revolution? its initial velocity is 0 radian per second and final 10 radian per second. It comes to this 10 radian per second in 2 seconds. How many revolutions does it do in 2 seconds? Five? 10? Well, it asked about theta, right? And theta is theta 0 plus omega 0 times t plus 1/2 alpha t square, right? Most general expression. Omega 0 times t. Remember the kinematics equations? Just x is equal to x0 plus v0 times t times 1/2 a t square. And you do the same in here. But since it starts from rest, you can take theta 0 and omega 0 as 0. So theta is 1/2 a alpha t square. What is alpha? Can you find alpha? Omega minus omega 0, right? Delta t. So omega 0 from rest, 0, to 10 pi radians per second. And divided by in 2 seconds. Right? So what is alpha? 5 pi radian per second square. So you can find theta run. Theta is equal to 1/2 alpha 5 pi. What is t? 2, 4. So theta is equal to 10 pi. Right? How many revolutions is 10 pi? 5 revolutions. Answer will be. I have to stop here. Okay. Let's continue on Thursday.